Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
What connection could possibly exist between a transparent safety visor and one of the most dangerous gases ever produced? The surprising answer is phosgene. Phosgene was once used as a chemical warfare agent. Yet today, inside highly controlled chemical plants, it is used as a raw material to manufacture polycarbonate, one of the toughest and most useful engineering plastics in the world. But the phosgene does not remain trapped inside the plastic. During the reaction, it is completely transformed. Its carbonyl group becomes part of the polymer chain, while its chlorine atoms leave the process mainly as sodium chloride, ordinary salt. So, how does industry safely transform basic chemicals into crystal-clear polycarbonate pellets at a scale of thousands of tons? Let us enter the plant. Polycarbonate, commonly abbreviated as PC, is a family of thermoplastics containing repeating carbonate linkages, oxygen, carbon, and oxygen connected around a carbonyl group. The most widely used engineering grade is bisphenol A polycarbonate. It was developed in the 1950s, and industrial production began in 1958. Unlike thermoset plastics, polycarbonate can be heated, melted, molded, and reshaped. A representative transparent grade has a density of around 1,200 kilograms per cubic meter, a tensile yield strength near 65 megapascals, and a glass transition temperature of approximately 144 degrees Celsius. A thin, clear section can transmit nearly 89% of visible light, close to glass, but with far greater impact toughness. That is why polycarbonate appears in vehicle headlamps, safety helmets, machine guards, medical equipment, electrical housings, optical components, and protective glazing systems. The conventional production chain begins with four important industrial chemicals: phenol, acetone, chlorine, and carbon monoxide. First, approximately 2 molecules of phenol react with 1 molecule of acetone to produce bisphenol A, or BPA, plus water. The two aromatic rings in BPA will later give polycarbonate its stiffness, strength, and heat resistance. In another completely enclosed unit, carbon monoxide reacts with chlorine to produce phosgene. CO plus Cl2 produces CoCl2. Because phosgene is extremely toxic, it is normally generated and consumed within a sealed, integrated production site. Continuous gas detectors, automatic isolation valves, emergency scrubbers, and closed transfer systems form multiple layers of protection. For perspective, the U.S. occupational exposure limit for phosgene is only 0.1 parts per million over an 8-hour period. The traditional manufacturing method is called interfacial polycondensation. First, BPA is mixed with an aqueous sodium hydroxide solution. The caustic soda converts BPA into a more reactive form called sodium bisphenolate. An organic solvent, traditionally methylene chloride, is then added. Water and methylene chloride do not mix, so two separate liquid phases form inside the reactor. Now phosgene gas is carefully introduced into the intensely agitated mixture. A small amount of tertiary amine catalyst accelerates the reaction. The key chemistry takes place at the enormous contact area created between the aqueous and organic phases. BPA units begin connecting through carbonate linkages. 2 molecules become 4, 4 become 8, and the chains continue growing until their molecular mass reaches tens of thousands of grams per mole. However, uncontrolled chain growth would make the resin too viscous to process. Therefore, approximately 1 to 3% of a monofunctional phenol may be added as a chain stopper. Because it has only one reactive end, it terminates the growing chain and helps engineers control molecular weight and melt flow rate. The simplified reaction is bisphenol A plus phosgene plus sodium hydroxide produces polycarbonate, sodium chloride, and water. The theoretical material balance is revealing. To create 1 kilogram of polycarbonate repeat units, the chemistry consumes roughly 0.90 kilograms of BPA, 0.39 kilograms of phosgene, and 0.31 kilograms of sodium hydroxide. It generates approximately 0.46 kilograms of sodium chloride. As the polymer forms, it dissolves in the organic phase, while the salt remains mainly in the water phase. This makes separation possible, but not yet simple. After polymerization, the reactor mixture enters a phase separator. The salt-containing water phase is removed for treatment and possible material recovery. This polymer solution is repeatedly washed with water and dilute acid to remove caustic, catalysts, salts, and unreacted chemicals. Next comes solvent recovery. Evaporators and condensers remove and recycle most of the methylene chloride. The remaining polymer is dried and passed through a vacuum-vented extruder, where traces of moisture, solvent, and volatile compounds are removed. The result is no longer a chemical solution. It is a clean, highly viscous stream of molten polycarbonate. Modern plants can also use a second route, melt-transesterification. Here, BPA reacts with diphenyl carbonate, or DPC, instead of directly reacting with phosgene. The process requires no methylene chloride reaction solvent and produces no sodium chloride byproduct. BPA and DPC are melted together with a very small quantity of catalyst. The first reaction stages may operate around 200 to 230 degrees Celsius under reduced pressure. As the chains grow, phenol is released. Continuously removing this phenol shifts the chemical equilibrium toward longer polymer chains. During final polycondensation, the temperature may rise to approximately 270 to 300 degrees Celsius, while pressure falls below 100 pascals, about 1/1000th of atmospheric pressure. This extreme vacuum is necessary because the polymer becomes incredibly viscous. Special reactors continuously renew the melt surface so that phenol can escape. A simulated industrial line producing 100,000 tons per year would average roughly 12 tons of polycarbonate every hour during 8,000 operating hours. The melt route avoids solvent and salt waste, but it presents another challenge. Excessive temperature or residence time can cause branching, degradation, and yellow color. Precise temperature, vacuum, and residence time control are therefore essential. Pure polycarbonate is only the starting platform. Manufacturers now adjust it for specific applications. UV stabilizers help prevent sunlight-induced yellowing. Antioxidants protect the polymer during processing. Mold release agents improve production speed. Flame-retardant additives are used for electrical equipment, while glass fibers can create stiffer structural grades. The melt passes through fine screen packs to capture contamination. It is then forced through a die as strands or directly cut in an underwater pelletizer. The pellets are cooled, dried, classified, and inspected. Quality laboratories measure melt flow rate, molecular weight distribution, color, haze, residual volatiles, moisture, and mechanical properties. Even tiny contamination can produce visible black specks or optical defects. For transparent components, cleanliness is not merely cosmetic, it is an engineering requirement. Polycarbonate's performance comes from a carefully balanced molecular structure. Its aromatic rings create stiffness and thermal resistance. The carbonate linkages provide polarity and strong attraction between chains. But the molecular geometry prevents the chains from packing into large crystals. The result is an amorphous polymer. Without large crystals to scatter light, polycarbonate can remain transparent. At the same time, its chains can rotate and deform under sudden loading, absorbing impact energy instead of allowing a crack to travel instantly through the material. This explains how polycarbonate can combine transparency, rigidity, and exceptional toughness, properties rarely found together in one material. But it is not perfect. Its surface can scratch, some solvents can cause stress cracking, and ultraviolet light can yellow unstabilized grades. If wet pellets are processed at high temperature, water can break polymer chains through hydrolysis. That is why a typical grade may need drying at about 120 degrees Celsius for 2 to 3 hours, with moisture reduced below 0.02% before molding. Polycarbonate manufacturing demonstrates both the power and responsibility of chemical engineering. The traditional process handles phosgene, caustic soda, and volatile solvent, so safe production depends on containment, detection, automatic shutdown systems, solvent recovery, and emergency scrubbing. The melt route reduces solvent and salt waste, while mechanical and chemical recycling technologies are increasingly being developed to return used polycarbonate into new products or recover valuable molecular building blocks. From phenol, acetone, carbon monoxide, and chlorine, industry creates long molecular chains that are transparent, heat-resistant, electrically insulating, and remarkably tough. A handful of clear pellets may look ordinary. But hidden inside them is precise reaction chemistry, high vacuum engineering, microscopic quality control, and one of the most impressive transformations in modern manufacturing. This is how polycarbonate is engineered at scale.